In this example, we're going to consider trying to push a crate on the floor and trying to see at what point do we switch from static to kinetic friction here. We'll start off by reading the problem statement and writing down some stuff that we can get from the problem statement. So we have from the problem statement the coefficient of static friction, μs, is equal to 0.7. We also have the coefficient of kinetic friction between these two objects is 0.6. And we have the mass of 20 kilograms. We apply this horizontal force P that changes depending on which of these situations we consider. And we want to know what's the frictional force in each case. So we do a free body diagram where we take away the person and replace them with that force P. And then we have weight acting down, normal force acting up, and the force of friction opposing the direction of impending motion or actual motion. So what we'll do is we'll check impending motion which is where you have the maximum force of static friction equal to μSn, to know whether we're using static friction or kinetic friction. And then we can calculate it based on that. So we've got our free body diagram. We can now apply Newton's second law. Sums of the forces are equal to mass times acceleration. And we can consider our two directions. We can consider the y direction, which tells us, here we've got y positive acting upward. So this will tell us that the normal force is acting up, the weight is acting down. Those are the two forces that are acting, and they sum to mass times acceleration in the y, which we would expect to be 0 as this stays on the surface. We can rearrange this equation to show that my normal force must equal the weight here, and the weight is equal to mg. So my normal force is equal to mg, 20 kilograms times 9.8 meters per second squared, which leaves us with a normal force of 196 newtons. So far, so good. Now we can check impending motion with the normal force. So checking that impending motion, we'll say my maximum static frictional force that could ever be exerted given this normal force is equal to μSn, or 0.7 times 196 newtons. So this means that the maximum frictional force that can be exerted here is 137 newtons. So that's our limiting case. We can now look at the x direction and see what actual force do we need here. So in the x direction, we'll apply Newton's second law, and there we can say P is acting to the right, F is acting to the left, so it's negative, and they sum to mass times acceleration. All right, so for part A, we push with 20 newtons. Our maximum static frictional force is 137. That's underneath the threshold, so our frictional force is exactly what it needs to be to balance that out and keep this crate from moving. Here, that says our frictional force is equal to 20 newtons opposing the direction of motion. For B, we check that it's the same thing. Frictional force is equal to just what it needs to be, 30 newtons. Part C, same deal. We're still under that maximum allowable frictional force, and so we end up with, I wrote the wrong thing. We end up with just enough frictional force to keep us from moving. And now for part D, it gets a little bit more interesting. In part D, we're exerting 180 newtons worth of force, and the maximum static frictional force is 137. So we're over that, it's going to start moving, and we'll actually have a frictional force that's less than 137 because it will be kinetic friction. So we have to calculate our force of kinetic friction. using mu k n. Luckily we have mu k, so we can plug that in. The normal force is the same as it was. And we get 117.6 newtons. I would probably round that to 118 newtons. And that is acting opposing the direction of motion. So we have our answers here. And we saw that the frictional force, when it was static friction, is exactly what it needs to be to maintain static friction up until the point where it can't do that anymore, in which case we change to kinetic friction. What about this x-directional equation? Here we didn't need that, but if I wanted to find its acceleration, in the case of case D where it starts accelerating, we can now plug things into there and solve for that acceleration in the x using Newton's second law in the x direction.